Okay, let's take a look at section 7.2 in the book, which is on a topic called volumes. And basically what we're looking at is if we take those regions we had before that were bounded by a curve and looking at them on an XY plane, if we rotate them around an axis or a line, what would the volume of that figure be? And we're going to use calculus to figure that out. So let's just look at an example here. So start with the curve y equals the square root of x. So we're looking at the function. And so far we know we can integrate the function and find the area that's under the curve. But what if we take that function and we rotate it around the x-axis? And sometimes these are kind of hard to picture. And there's some software we can look at online that'll help you generate these images. But basically, if you see this picture, if you take this line and you rotate it around the axis, do you see that you get this sort of, I don't know, it almost looks like a bowl turned on its side. And what we want to know is how to figure out the volume of that figure. So instead of thinking of it as slicing in little rectangles like we've been doing in 2 dimensions, we're still slicing it. You can think of it as slicing it, but now it's not going to just be a rectangle, it's going to be like a little disc. So if I slice through this, it's going to create this little 3-dimensional disc. And each one of those discs is a cylinder. And you might have to kind of turn your head sideways so you see it. But each one of those discs is a really tiny cylinder. So the cylinder, we can figure out the volume of a cylinder. We know how to do that from geometry. The volume of a cylinder is pi r squared times the height. So volume, of course, would be pi r squared h. H is the height. In this case, the height, and again, you might have to kind of turn your head sideways to visualize what I'm talking about, but the height of this little cylinder, this little cylindrical disc, is just the thickness of the cylinder, which we can think of as a small change in x, and that's going to be our dx in just a minute. The radius, on the other hand, is the y value of the function. So what do I mean by the radius? If you think about going from the x-axis out to where it hits the graph, that would be the radius of that cylinder, right? Or that if you think about looking down at the top, you have a circle. So the radius of that circle would be the y value. And so the y value, of course, is the function given by the square root of x, because remember, y equals the square root of x. And the thickness, we said, is a real small change in x, so we're going to call that dx. How many of these cylinders do I have? Well, I've just sliced sort of a generic one in the middle, but I have an infinite number of cylinders that make up the volume of this figure. And so the idea is we want to add those up. So in calculus, how do we do that? We don't add each one by hand, of course. We're going to use an integral to do that. So what we have is the integral of the function from 0 to 4, y0 to 4, because I'm integrating with respect to x, and I wanted the volume to be from 0 to 4. Go back to the original picture. We stopped at 4, and that's where we rotated it. So where this would have hit the x-axis was at 4. So we're going from 0 to 4 of pi times the radius squared dx, and the radius was the function itself, square root of x. And then we're going to use the fundamental theorem to integrate this. So we've got pi times x squared over 2 from 0 to 4. Calculate it, we get a value of 8 pi. So that's the volume of this 3-dimensional figure we got when we rotated. How do we know this works? Let's try this with something a little bit more familiar. So I'm looking at the line y equals x. And if we want to rotate this around the x-axis, picture what that would look like. It would give us a cone, right? Can you visualize that? If we take this region and we rotate around the x-axis, we're going to have a cone turned on its side. So using calculus, the volume of this cone would be, and by the way, pi is a constant multiple, so you can always move that to the front of your integral symbol. And generally when I do these, that's what I do. I might do it in the beginning, I might do it in step 2, but remember pi is a constant, so you can move it to the front of your integral. So I've got pi times the radius squared, so in this case the radius is the function itself, x, dx, from 0 to r, because r is where we cut it off. So fundamental theorem, that's x cubed over 3 times the pi, of course, constant multiple from 0 to r. And so if we plug in the r and then plug in 0, of course, we get 0. So we get 1/3 pi r cubed. You may or may not remember, but this is the formula for the volume of a cone. And it's okay if you don't remember it, not a big deal. But the volume of a cone from geometry was pi r cubed times 1/3. And so this worked okay as long as the radius is a constant, like a line, that's a constant. The slope would be constant, right? So it doesn't change. The problem is, though, when we get into stranger looking functions, that's where the calculus comes in, why we have to use the integral. So this method of slicing into these small disks or these small little cylinders is called the disk method. And in general, we can think of it as, to find the volume using disks, we can think of it as pi times the integral of the function from a to b, whatever the limits are, of the radius squared dx. This will work as long as we're rotating around a horizontal axis. I'm using the x-axis so far as my examples, but it doesn't always have to be the x-axis. It could be any horizontal line. As long as we're going around a horizontal line, we're going to integrate with respect to x. Now, if we go around a vertical line, things change. If we're going around something that's vertical, we're going to use the y-axis. And so, we're going to integrate with respect to y. So for example, if we rotate around the y-axis, everything turns to y. And that would be the same for any vertical axis of rotation. Always draw a picture when you do these. That's really important. Don't try to figure out whether it's x or y, which one you're integrating with respect to, unless you have a picture. Draw a representative rectangle to find the axis of, around the axis of rotation, and decide if it's a disk or a washer. Now I'll talk about washers again in just a minute, so hang on to that term. So far we've just looked at disks. Washers come into play when there's a hole, and we'll do an example in a minute. And then once you've just made that decision, go ahead and set up your integral. All right, so let's look at this one. The region between the curve x equals 1 over the square root of y, and they're limiting you from the interval y goes from 1 to 4 and the y-axis. We're going to draw a picture and look at this region, and we're going to rotate it around the y-axis. So you can use a calculator or use Desmos to figure out what this picture looks like. I wouldn't necessarily know what 1 over the square root of y looks like. Actually, I take it back. I don't think you can put this in your calculator because it's in terms of y, but you could use Desmos. So remember to do that when you're working these problems. So here's what this function looks like just from the integral, or the interval from 1 to 4 for the y values. So we want to rotate it around the y-axis. So it almost looks kind of like a lampshade to me. You're going around the y-axis. It's a vertical axis of rotation, so that means that we're going to integrate with respect to y. So your little disk is going to be sliced this way now. It's going to be perpendicular to the y-axis. So that means it's going to be dy, we know that, and the radius for that disk is going to be the function itself, 1 over the square root of y. So when we put this together, we have pi times the radius squared, right? The function itself is the radius, dy. And we're going from 1 to 4 because that's the region they told us to restrict it to in terms of y. So then we're going to integrate that, clean it up a little bit first, move the pi to the front probably, and integrate that. And by the way, I just realized something. Integral of 1 over y, we actually haven't done that yet. We didn't do that in our Calc 1 class. So you don't know how to integrate 1 over y. Don't worry about it. We're actually going to do it in the next section, next couple of sections. But for now, take my word for it that the integral of 1 over y is the natural log of y. But with that knowledge, you can solve it from there. So we want to use the fundamental theorem of calculus, so we're going to evaluate it at 4, and then evaluate it at 1, and take the difference. Natural log of 1, of course, is 0. So we're left with natural log of 4 times pi. I don't know why the author of this PowerPoint wrote that 4 as 2 squared. I guess so they could put the 2 in front. That is not a necessary step. You could have just left it as pi times the natural log of 4. That would have been your volume. Okay, let's give this one a try. Find the volume of the solid formed by revolving the region bounded by the function f of x equals 2 minus x squared. So we know that's a parabola that opens down and shifted up 2 units. And the line g of x equals 1. So that's just the horizontal line through y equals 1. And we want to rotate it about the line y equals 1. So on these problems, they always have to tell you what the region needs to be bounded by and what they want you to rotate around. So they always have to give you that information. So draw a picture. Note that the two graphs intersect at x equals -1 and x equals +1. All right, so if you can kind of picture what this looks like, if we rotated, we're looking at this region in purple because that's what's bounded by what they told us, the parabola and the line. So it's this region in purple. We're rotating it around the horizontal line, y equals 1. And so here's what you want to think about. This is a disk because there's no gap, and we'll talk about washers in a minute, but there's no gap between the purple region and the line I'm revolving around. Do you see that? The purple region touches the line we're going around the entire time. So we're going to use the same formula, pi times the radius squared, and I'm using dx because we're going around a horizontal axis of rotation. Here's what's a little different about this one, though, because I'm not just going around the x-axis, I'm going around the line y equals 1. The radius, to get the radius this time, just like we did in the last section, I have to do the top minus the bottom. That's going to be my radius. So what I did is I did 2 minus x squared minus 1. That's the radius. So we have pi times the radius squared dx. And we're going from -1 to 1 because those are the points of intersection in terms of x. And again, we're going in terms of x because it's a horizontal axis of rotation. So I'm going to simplify that. I'm going to FOIL it out. I'm going to use the fundamental theorem. I'm going to integrate. And here's my result. I'm going to skip the details for now. I want you to focus on the setup and the process. Okay, let's look at this figure. So we've got the region bounded by the line y equals x squared and y equals 2x. And this time we want to revolve around the line y, or about the y-axis. So kind of, first of all, get a picture. Make sure you sketch this. So we're looking at the parabola y equals x squared and the line y equals 2x. We want to rotate around the y-axis. It's kind of like a bowl shape, and it's empty in the middle because you notice there's a gap between the region that I'm interested in and the line that I'm rotating around. So now this is a little bit different because we have a gap or a hole in between the line we're rotating around, which remember is the y-axis, and the region we're rotating. So this time we're going to use what's called the washer method. You see that if we do a horizontal slice, there's a hole in our disc. It's not really a disc anymore. It's not a filled-in cylinder like it was to begin with. We've got a hole in the middle of it. And do you know what a washer is? A washer is like a small tool, not a tool, but a small, well, it is a tool. You might see it at a hardware store, but it looks like this. It looks like a small donut almost. There's a hole in the middle. That's called a washer. That's where this name comes from. So we have a hole in the middle. All right, so the difference this time is now we have what's called an outer radius and we have an inner radius. So here's what's new. We have an outer radius and an inner radius. The outer radius is the function that's further away from the line that we're revolving around. So in my example, the outer radius is the x squared function. The inner radius is the line 2x. So the outer radius is going to be the x squared. The inner radius is the 2x. And the thickness is still going to be, the thickness is going to be dy in terms of dy. So we got to put all this in terms of dy. Why does this need to be in terms of dy? Because we're going around a vertical line. The main thing that I want you to see is because of that hole, we have to have two radii, an outer radius and an inner radius, and the outer is the one that's further away from the line we're rotating. Let's put all this in terms of y because it's a vertical axis of rotation. So y equals x squared turns into x equals the square root of y. Make sure you see I just take the square root of both sides. Y equals 2x, divide by 2, we get x equals y over 2. So let's put all this together. So we have the integral from 0 to 4, y0 to 4, because those are the limits of integration in terms of y. I'm going from 0 to 4, of the outer radius squared minus the inner radius squared. Everything's in terms of y, and then don't forget the pi. Pi, of course, can be moved to the front because it's a constant multiple. And then I clean this up a little bit. I'm going to use the fundamental theorem of calculus and get my volume, and it's 8 pi over 3. So the takeaway from this example, we used a washer method because we had a hole in the middle of what we were rotating. So we've got an outer radius and an inner radius. The outer is the function further away from the line we're rotating. The inner radius is the function closer to the line we're rotating around. And everything was in terms of y because we were using a vertical axis of rotation, the y-axis. So here's kind of the general rule. If we're dealing with a washer, if there's a hole, you're going to have the outer radius squared minus the inner radius squared times pi, of course. And again, you got to think about if it's a vertical axis of rotation, we integrate with respect to y. If it's a horizontal axis of rotation, we integrate with respect to x. And I think I'm going to stop with this example, and we'll do some basic ones together when we meet on Monday and do some more examples together.